Welcome back. Now it's time to pause to solve some exercises before we continue the lecture. So we're going to solve in this video the first three exercises of chapter 1. First exercise, we have to prove what is known as the second form of the triangle inequality. So if you have a distance d on a metric space on a set X, then we have to show that the difference between dxy and dxz in absolute value is at most dyz. Okay, so this looks really like the triangle inequality, but we have absolute values. Okay, so if you don't know where to start, one way is to start with what we want to prove and see where this leads us to. Okay, so let us rewrite what we want to prove. Okay, this is very useful. Okay, in problem solving. So this inequality is actually a double inequality, because if the absolute value of a number is less than another number, then the number is between minus. So the difference is between minus dyz and dyz. Okay, this is, as you know from school. So, but this is actually a double inequality. So if you look at this part of the inequality, dxy minus dxd is less than dyz, and the second one, minus dyz, is less or equal than dxy minus dx. Okay, so these are equivalent actually. Okay. Now, if you add dxz to this inequality, you get dxy less or equal than dxz plus dyz. Okay, and now if you add dyz and dxz, you get dxz less or equal than dxy plus dyz. And you should recognize here that these two inequalities express the same inequality, which is the triangle inequality. Okay, but with different symbols. So what we want to prove is actually equivalent to something true. Okay, and therefore this proves the second form of the triangle inequality. Okay, so very, very easy. Now, there's another way to write the proof. We start with the usual triangle inequality, and we subtract dxz. So we get dxy minus dxz less than dyz. Okay, very good. Now, but x and y and z are arbitrary. So if I interchange the roles of z and y, we get dxz minus dxy is less than dzy, which is dyz, same thing. And so, and this implies actually that the absolute value of the difference is less than dyz, because the absolute value of the difference is either this, if it's positive, or the opposite, which is this one, if it's negative. So this implies the result. And actually, you observe that we have equivalence. So actually, form 1 is equivalent to form 2. Okay. So we can replace in the third property, the triangle inequality, we can replace the triangle inequality by this one, by the second form. Okay. So this concludes exercise 1. Exercise 2, we have to find the intersection of all balls with the same center and the union of all balls with the same center, closed and open. Okay, here it's good to start by drawing a picture. Okay, so here we have a decreasing collection of balls, and you see that when the radius becomes smaller and smaller, the ball shrinks to the center. So we conjecture that the intersection is equal to the center. And now we prove that. How do we prove that? Double inclusion. Okay. One way is clear, because A is in any ball of center A. So it's in the intersection. Okay, so the singleton A is contained in the intersection. Conversely, we take an element in the intersection and we prove that it must be here, so it must be equal to A. So if X is in the intersection of all these balls, then it belongs to be AR for every R, and therefore its distance to the center is less than R for every R. And so if we let R tend to 0, we get dxa at the limit, we get dxa less or equal than 0. Okay, or there's another way to see that. If a number is less than any positive number given in advance, then it must be 0. Otherwise, we get a contradiction. But dxa is bigger or equal than 0, therefore dxa is exactly equal to 0. So by the second property of the distance, x is equal to A, and so x belongs to the singleton A. And now we prove similarly that the intersection of all closed balls of center A is also reduced to the center. So same proof, actually. So instead of less or equal, less, we have less or equal. So it doesn't change anything. And here's an interesting consequence of this identity. We know that a closed ball is a closed set, and an intersection of closed set is a closed set. Therefore, the singleton A is closed. We proved that in the lectures in a different way. But here we have another proof that in a metric space, singletons are closed, and therefore finite sets are closed. Okay, third identity, union. Okay, try to draw an increasing collection of balls with the same center. Intuitively, when the radius becomes bigger and bigger, the ball covers a bigger and a bigger part of the space. So we conjecture that the union is the whole space. How do you prove that? Double inclusion. One inclusion is trivial because BAR lives in X, so BAR is in X, so the union is in X. So trivial. Conversely, we take an arbitrary element in the space, small x, and you have to prove that it's in the union. So it's in one of them. Now, this is trivial also because we can always find a number R bigger than the distance between X and A. This is a property of the real numbers. Okay? No matter how big the number gives me, I can find a bigger number. So, and if dxa is less than R, then this means that X belongs to the ball of center A and reduce R for this R. Okay, and therefore X is in the union. And that's it. So we have double inclusion. And part D is completely similar. Instead of bigger, we can write R bigger or equal, and therefore we have the same thing. Okay, so this concludes exercise 2. Exercise 3, very important actually, and we can use the results of this exercise in the exam or in the lectures later. Okay, so first property is that if A is contained in B, then the interior of A is contained in the interior of B. Second property, the intersection of the interiors is the interior of the intersections, finite of course, because we just have two. And the union of the interiors is contained in the interior of the union, but equality may fail. It may hold, it may fail. You have to give examples, okay, from the list of examples that we learned. And you have something similar for the closure, okay, but with the closure, I take unions instead of intersections. So we have equality when you have union and just one inclusion when you have intersections. Okay, so the first part is very easy. The interior of A is always contained in A by definition because it's by definition the biggest open set contained in A, so it's contained in A. And since A is contained in B, then a circle is contained in B. So, but A circle is an open set. So we have an open set contained in B, but B circle is the biggest open set contained in B, and therefore it must contain a circle. So, trivial. Second property, okay. A circle is contained in A, and B circle is contained in B. So the intersection of A circle and B circle is contained in A intersected with B, but this is a finite intersection of open sets, so it's an open set. Okay, it's an open set contained in A intersected with B, but the interior of A intersected with B is the biggest open set, so it must contain this one. So this is one way. Now, conversely, the intersection is contained in A. So according to property A, proved in A, the intersection of A with B is contained in the interior of A. And same thing, the intersection is contained in B, and therefore the interior is contained in the interior. And therefore, this set here is contained in both A circle and B circle, and therefore it's contained in the intersection. And therefore, we have the reverse conclusion, and therefore equality. Okay. Third question. Of course, we look at the biggest. We compare A and A union B. A is smaller than A union B, so the interior is contained in the interior, and same thing, B is contained in A union B, so the interior is contained in the interior. So the union of these two is contained in the same set. So this is what we want to do. Now, less trivial is to find examples where equality holds, examples where equality fails. Okay, so examples where equality holds can be very easy to find because it's just enough to take a trivial case. So for example, if one of them contains the other, if B contains A, then what happens? Then A union B is just B because it's the biggest. Okay, so A union B circle is just B circle, and A circle union B circle is B circle as well because A circle is contained in B circle. Okay, so this is very. And another trivial case is when both A and B are open. If both are open, then the two sides are equal to just A union B, because A circle is equal to A if A is open, and B circle is equal to B if B is open. And since A union B is open as well as a union of open sets, it's equal to its interior. So you can always find trivial examples. A little bit less trivial, take two separated sets. So they are separated by some distance. So 0, 1, take A equals 0, 1, and B equal to 3. You can take them closed or open, doesn't change anything actually. Then the interior of A is 0, 1 open, the interior of B is 2, 3 open. Therefore, A circle union B circle is 0, 1 open union 2, 3 open. A union B is 0, 1 closed union 2, 3 closed. And you can easily check that the biggest open set contained in A union B is just this one, 0, 1 open union 2, 3 open, exactly as we did in the lectures. Okay, because this is an open set and it's contained in A union B, but anything bigger, strictly bigger, will not do, because if I add one of these endpoints, 0, 1, or 2, and 3, it's not open anymore. So this is really the biggest open set contained in A union B. Okay, and the idea here is that A and B are in some sense far apart, okay? And the right assumption is this one. A doesn't meet B bar and B doesn't meet A bar. So this in particular implies that A and B are disjoint, but this is stronger than saying that just A and B are disjoint. Okay, this could be a challenging exercise, okay? So you assume this condition. How do you prove the reverse inclusion? You take an element in the interior of A union B and you prove that it's either in A circle or in B circle. Okay, I'll give you a hint. If X is in the interior of the union, then it's in the union. So it's either in A or in B. And now you have to prove that if it's in A, then it's necessarily in A circle. And if it's in B, then necessarily it's in B circle. How do you prove that? By using this condition. If X is in A, then it cannot be in B bar. And now use proposition 1.8. What does it mean to say that X is not in B bar? It means that there is an open neighborhood of X not meeting B. Okay, so try to relate all these ideas together. Now, examples where equality fails. Take two sets that do not satisfy this condition. So they meet, for example, 0, 1 closed and 1, 2 closed. Okay. Of course, you could take, for example, 0, 1 and 1/2 2. Same thing, doesn't matter actually. Okay, so if we take A equals 0, 1 and B equal 1, 2, then A circle is 0, 1 open, B circle is 1, 2 open, so the union is just 0, 1 union 1, 2 open, so it's just 0, 2 without 1. However, if you take A union B, you get 0, 2 open, so they differ by 1 point. Of course, this is contained in that one, but strictly. So we don't have equality in this case. Now, if you recall the fundamental examples of interiors that we encountered in the lectures, you will come up with an extreme example. If you take A to be the rational numbers and B to be the irrational numbers, then what happens? Then we know that the interior of A is empty and the interior of B is empty. So this side is empty. However, the union of A union B is the whole line R, and its interior is R because R is open in itself. So we have an extreme case here. One side is empty, the other is the whole space. Okay, so this concludes, and of course you can give other examples if you like. Now, fourth question, we have to prove that is A is contained in B, then A bar is contained in B bar. This is just parallel to the first question. B is contained in B bar always. And since A is contained in B, then A is contained in the bigger one, which is B bar. So what do we have? We have a closed set. This is a closed set containing A. But by definition, A bar is the smallest closed set containing A, and therefore it must be contained in B bar. So trivial. Now, union, this is not difficult. Of course, we look at the biggest. We compare A and A union B. A union B is bigger, so the closure contains the closure, and same thing with B. So A bar union B bar is contained in A union B bar. Now, conversely, A is contained in A bar, B is contained in B bar, so the union of A and B is contained in the union of A bar and B bar. And now this is a closed set because it's a finite union of closed sets. And the closure of this guy is the smallest closed set containing A and B. So A bar union B bar contains A union B bar, so we have the reverse inclusion. Okay, now last question about the intersection of the interiors. The intersection is smaller than A and smaller than B, so the interior of this guy is contained in the interior of A and it's contained in the interior of B, so it's contained in the intersection of the interiors. And this is okay. So this proves the inclusion. Now, examples where we have equality. Think of some trivial cases. If one of them contains the other, for example, if B contains A, then the intersection is the smallest set, which is A. So A intersected with B bar is just A bar, and A bar intersected with B bar is also A bar because A bar is contained in B bar. So you may easily check that we have equality and both sides are equal to the closure of the smallest set. Okay, another trivial case is when both A and B are closed, of course, because then A equal A bar, B equal B bar, A intersected with B. So A intersected with B is closed, so it's equal to its closure. So everything is equal to A intersected with B. Okay, less trivial example. Well, also trivial, but if this biggest, so if A bar doesn't meet B bar, then of course A doesn't meet B. So both sides are empty actually in this case. This is an extreme case. And in parallel to the last example of the third question, we have equality if A union B circle cover the whole space and B union A circle covers the whole space. Okay, this is just the parallel condition of the last one. Okay, this can be a little bit challenging, but it can be deduced from example 4 and the examples of question C. Now, examples where equality fails. Take, for example, A to be 0, 1 open and B equal 1, 2 open. In this case, the intersection is empty, whereas A bar intersected with B bar is 1. So we have a strict inclusion here. Don't have equality. One is empty, the other is 1. And another extreme case is the rational numbers, take A to be the rational numbers, B the irrational numbers, then they don't meet, so the closure of the intersection is empty, whereas the intersection of the closures is just R intersected with R, which is R. So one is empty, the other is the whole space. So, and you may also invent other examples if you like. Okay, so this concludes exercise 3 and the video as well. So in the next video, I'm going to solve exercises 4 to 8. So thank you for your attention and see you next time.